So when we're doing ANOVA, we're doing a hypothesis test. We're basically asking if those alphas are different than 0. So in Stat 220, we had our null and alternative hypotheses for ANOVA, and they were like mu1 is equal to mu2 is equal to all the way out to mu sub I guess we would do. And here we would have at least one mu sub I not equal to mu sub j, so at least two of the means were not equal. But now that we're getting a little bit more sophisticated with how we're writing out our hypotheses, it's not that we're asking, are the means equal? We're basically asking, like, are any of the means different than the grand mean? Because these alphas, these are the group effects, the difference. We're saying our null hypothesis is all of the means are the same as the grand mean. All of the group effects are 0, and the alternative is at least one of those group effects is not equal to 0. So with this espresso example, I ran the AOV command to get the ANOVA table here, and I got a very small p-value, 4.7 times 10 to the minus 7th, or 0.000004 it is. So it's a really small p-value. We have a really small p-value, which would mean we would reject the null hypothesis. And we have evidence to suggest at least one mean is different than the grand mean. So I gave you the grand mean here, 44.5, and we had all of the individual means here. We would have to do some comparisons to see which one of these are actually different, but we know at least one of them is different than the grand mean at this point. And then the conditions for ANOVA are the INE conditions. There's no L anymore because it's not a linear model. We've got different means that we're doing predictions for each group. So we've got the independence condition. That's still the thinking condition. But now you need to think about independence between groups and independence within groups. So are all the individuals, like all the espressos within the bar method, are they independent from one another? Were they independent draws or trials or experiments? And then is there independence between the groups? Or is there some relationship between bar method and hyper espresso method, or espresso system and bar method? So that's the thinking condition. Normality, you're still going to check with a QQ plot, and you want it to be nice and close to that line. And equality of variance means you need equal variance in your groups. And you can look at the residual versus fitted plot. We looked at some of them last week, and you're looking for how tall or short those bands of residuals are. But it's often easier to just check the standard deviations for the groups, and our rule of thumb is we want the SD max divided by the SD min to be less than or equal to 2. So in this case, my maximum standard deviation was 10.1, and I divide that by 7.3, and I think that's 1.38, and that's less than or equal to 2, so we've got the equality of variance here. All right, so our conditions are met. We rejected our null hypothesis. We might be interested in doing inference after ANOVA. So we'd like to know, okay, at least one of those group effects is significantly different than 0, but which one? Which of the pairs are different? Which of the individuals are different? And so this can lead to the problem of multiple testing. So the problem of multiple testing is if you do a lot of t-tests, for example, to make comparisons between groups, say you do 20 t-tests and you set your alpha level at 0.05, that means that we expect to make a mistake 1 out of 20 times. And so even if there's nothing going on, if you do 20 t-tests, you're probably going to find one that looks significant just by chance. So we've got a few solutions to this problem. We've got Fisher's least significant difference, which gets abbreviated LSD. We've got Tukey's honest significant difference, which is abbreviated HSD. And we've got the Bonferroni correction. So The main thing that you probably want to do after ANOVA is to do a confidence interval, either a confidence interval for a single mean or a confidence interval for a difference in means. And so you might be interested, is this difference in means, does the interval cross 0? If it doesn't, then probably there is a significant difference between those two groups. Or you might just be interested in what a range of values could be for a particular mean. So the way that you do this is you find your point estimate, which is your y bar for the group or for the difference of two groups if you're doing a difference in means. And then you add a margin of error. And the margin of error is that something that depends on the distribution and the alpha level, so maybe a t-star value, times the standard error. And in this case, the standard error is going to be the square root of the mean squared error over n sub I, the size of that group. Or if it's a difference in means, the square root of the mean squared error times 1 over the sample size for the first group plus 1 over the sample size for the second group. And that MSE is going to come from the ANOVA table. You know the y bars from the data, you know the n's from the data. The t-star, that's the tricky part. So this is the thing where you'd need to know the correct degrees of freedom, and you'd need to know your alpha level. And this is where those corrections come in. So Fisher has this thing called the least significant difference, and with that one, you would find your t-star according to alpha and n minus k degrees of freedom. Then we've got Tukey's honest significant difference. So Tukey was kind of clapping back at Fisher and saying, well, my difference is actually honest. And this is probably the most complicated, where you'd use a critical value. It wouldn't exactly be t-star. It would be q over the square root of 2, and q would depend on the studentized range distribution. And then the Bonferroni approach, you choose the t-star according to alpha divided by m with n minus k degrees of freedom. And m is the number of tests that you're doing. It's k choose 2. So my favorite of these methods is Tukey's HSD, because I'm a huge fan of John Tukey, and also because it works really easily in R. You need the agricole package for this to work, but then you can just run Tukey HSD on a model object, and it will do all of the computations for you. So the thing you probably want to focus on are the lower and upper, and these are the confidence intervals for the differences. So the hyper espresso method minus the bar method, we're 95% confident it's between 18.9 and 38.9. So we're pretty sure that the hyper espresso method is better in terms of the foam. Then the next one, the interval is negative 2.7 to 17.3. That includes 0, so this would be not significant. And then the last one, negative 31.6, negative 11.6. That one is significant, and this one is negative. So that means that when we do espresso system minus hyper espresso method, the hyper espresso method must be bigger for that subtraction to turn out negative. So we're saying that the hyper espresso method is better here. So hyper espresso is better than VAR. Hyper espresso is better than espresso system. So if I had to pick one, I would pick the hyper espresso method. So that's about confidence intervals. P-values get really tricky with some of these outputs. They get adjusted in particular ways that I'm not even sure behind the scenes what R is doing. You can just look at them as if they were regular P-values and use your normal alpha equals 0.05 cutoff. So they've been adjusted ahead of time for you, but it's probably easier, rather than thinking about a P-value, to think about an effect size. So an effect size, it's an alternative to p-values, which is going to try and make the difference between practical significance and statistical significance more apparent. So for a single mean, the effect size, which is Cohen's D, so it's denoted D sub I, would be the difference between the mean for the group and the grand mean. In other words, the observed alpha alpha hat of I, the group effect, divided by the square root of the mean squared error. And for the difference in means, we would do the difference in those two group means divided by the square root of the mean squared error. I did some computation here. I need to go remind myself of what that was. So that was the difference from right here, the difference between the hyper espresso method and the bar method. It was 28.9, so that could be the difference for the top. And then I divided by the square root of the mean squared error from my ANOVA table, and I got an effect size of 3.4 between those two groups. This number tells you something about how much the groups differ in terms of standard deviations, more or less. And so this is as if they differ by 3.4 standard deviations. That's a big effect size. So I think the rules of thumb are usually like 0.2 is a small effect size, 0.5 is medium, and greater than 0.8 is a large effect size. So this is a pretty big one. And that's borne out by that interval that didn't contain 0 and was really far off from 0, and also this adjusted p-value, which was really small.